Booting intro. Mr. Vaughn's classroom. Math made cheesy? No, math made easy.
Welcome back to Mr. Vaughn's classroom, where math is made easy. In this video, we're looking at Unit 3 on Similarity. This is Lesson 8, Are They All Similar? The learning goal for this lesson is to prove figures are similar. We do have two learning targets in this lesson. The first says that I can critique proofs that use similarity, and the second learning target says that I can write proofs using the definition of similarity. We do have one glossary term for this lesson, and that is similar. One figure is similar to another if there is a sequence of rigid motions and dilations that takes the first figure on to the second. Triangle A prime, B prime, C prime is similar to triangle ABC because a rotation with center B followed by a dilation with center P takes ABC to A prime, B prime, C prime. So we're starting with the small blue triangle. We are rotating around point B to create the small red triangle, and then we are dilating with center P to turn the small red triangle into the large green triangle. Because we can do this with nothing other than rigid motions and dilations, then the two triangles are similar. Not congruent, but similar. Now that we're done with the introduction, let's go ahead and take a look at these practice problems.
You kids have it easy. Back in my day, we didn't have calculators. We had to use our noggins.
Practice problem number 1. This is an invalid proof that all isosceles triangles are similar. Explain which step is invalid and why. So remember that an isosceles triangle simply means that two of the three sides are the same. So a couple of common ones that we could draw here would be a right triangle where we have a 90-degree angle and two 45-degree angles. And then we could also draw an obtuse triangle and let's say that's 120 degrees and then 30 degrees each. So we've drawn two isosceles triangles, and we're going to label one ABC, and we want to make sure that AC and BC are the same length. So we're going to say this is A, B, and C. And then we're going to label the other one DEF, and we want D and F to be equal to EF. Okay, so we have our two isosceles triangles here. Number 2 tells us to dilate the triangles to a new triangle, or dilate the first one, ABC, to a new triangle, A prime, B prime, C, using C as the center, and a scale factor where we say that side DF over side AC. That way we end up with A prime C equals B prime C also equals DF and EF. So let's just go ahead and change this to A prime and B prime. And let's just say all the sides are now the same length. They're all a length of 5 units. Now, they want us to translate by a directed line segment, CF. So we're going to move it this way. And this way we can take A prime, B prime, C to a new triangle, A double prime, B double prime, F. So let's go ahead and put this new triangle in here. So this is our right triangle with a 90 degree and two 45 degrees. And this is now A double prime, B double prime, F. So now we've moved the original left red triangle over here to where I have this blue triangle now. And our sides are still the same. We're still going to say that we have these side lengths that are each 5. So now step 4 says that if A double prime F is 5, and that equals DF, which is 5, then we can rotate using F as the center. And so we'll rotate this blue triangle this way so that we can line it up with DF. And now over here, A double prime F would lay directly on top of DF. Then step 5 says that since B double prime F is 5 and EF is 5, then we could rotate it this way and set it directly on top of EF. And we can do that, but notice what happens. Even though our left side and our right side of both triangles is 5, the angles are different. That means that DE is not the same length as A double prime, B double prime. So what we end up doing is we rock that blue triangle over to the left so that it lines up, but now our right side doesn't line up. And then in step 5, we rock it back over the other direction so that our right side lines up, but our left side doesn't anymore. And so then step 6 says we've now established a sequence of dilations, translations, and rotations that takes A to D, B to E, and C to F, so the triangles are similar. Well, the problem with that is step 5. So step 5 takes B double prime to E, but it doesn't keep A double prime on D. Now, because of this, the two triangles do not line up. They do not fully line up. So they are not similar. Okay, if the angles start out different, then simply doing rigid transformations and dilations cannot make them line up. Remember, even though your side lengths can change size as long as they remain proportional, the biggest part is your angles still have to be the same size. And when your angles start out different, it doesn't matter if you make the side lengths bigger or smaller, your angles aren't changing. So there's no way that a triangle with 90, 45, and 45 is ever going to line up with a triangle that's 120, 30, 30. Because I can make those triangles smaller, I can make those triangles bigger, but the only thing I'm really changing is the side lengths. I'm not changing those angles. So those angles are never going to line up with each other. I hope this helps you make sense of this. But if you do still have any questions, go ahead and leave a comment below.
We're going to have so much winning, you'll get tired of winning. You're going to get tired of solving all these fantastic problems.
Practice problem number 2. Which statement provides a valid justification for why all circles are similar? So let's look at choice A. All circles have the same shape. They're all a circle. So they must be similar. Well, we can reference just back to practice problem number 1 to see that this is not true, because we just proved not all triangles are similar. So if we literally just proved that not all triangles are similar in the previous practice problem, then just because circles have the same shape doesn't prove that they're similar. So A cannot be the correct answer. Now let's look at option B. All circles have no angles and no sides. Therefore, they must be similar. Well, circles do have angles. Circles have 360 degrees. That is an angle. It's one angle, and it's all the way around the circle, but it is an angle. And to say that they have no sides, they wouldn't exist if they didn't have a side. They do have one continuous side. So this statement that they have no angles and no sides just isn't true. A circle has 360 degrees and it has one continuous side. Therefore, B cannot be the correct answer. So we're down to option C. It says I can translate any circle onto another, so they must be similar. Well, the key here is that we're saying that we can translate. When you translate, you're not changing the size. So you can't translate different size circles onto each other. If I have a smaller circle and a larger circle, and I move one to the other, they're not going to be right on top of each other. I need to dilate them. So to say that I can simply translate any circle onto any other circle just doesn't work, because if they're different sizes, they're not going to translate onto each other. So C cannot be correct. So that leaves us with D. And D says that I can translate the center of any circle to the center of any other circle, and then dilate from that center by an appropriate scale factor, so they must be similar. This is true. If I take the center point of any size circle and I move it to the center point of any other size circle, then all I have to do is make one of the circles bigger or smaller until they fit onto each other. So D is the statement that is correct. So with questions like this, we want to be very careful with the words that they're using and how they're saying things to determine whether it is a valid justification or not. I hope this helps make sense of this to you, but if you do have any questions left, please feel free to go ahead and leave a comment below.
Here we go, folks. We've got a real barn burner of a math problem on our hands today. Let's see how this equation plays out.
Practice problem number 3. Which pair of polygons is similar? So we need to make sure that the angles are the same and the side lengths are proportional. So let's look at A. We can see that they each have a 90-degree angle. So we could go ahead and believe that the other angles are similar. So we need to check the side lengths and see if they're proportional. Now, based on where the angles are, this side length of 12 should correspond to this side length of 4. And if we take 4 and multiply it by 3, we get 12. So our scale factor could be 3 or 1/3, depending on the direction that we're going. Now we could say that this side length of 5 corresponds to this side length of 3. So let's try and multiply 3 by 3. And the problem is that we get 9 and not 5. And then finally, this side length of 13 should correspond with this side length of 5. So if we take that side length of 5 and multiply it by 3, we get 15, not 13. Since the sides are not proportional, A is not similar. Now let's look at B. On B, we can see that we have 4 90-degree angles. But when we look at its partner shape, we do not see these marked as 90 degrees. Because the angles are not similar, then the figures or shapes themselves are not similar either. So B is not going to be a correct answer. Next, we can look at C. I look and notice that I have 4 90-degree angles on the left. I have 4 90-degree angles on the right. So our angles are all good. Now I need to see if the side lengths are proportional. And on the ends, we have side lengths of 1 and side lengths of 2. So I could say that 1 times 2 equals 2. So that should be my scaling factor. Then, on the top and the bottom, we have side lengths of 5 and 10. And if I multiply 5 times that scaling factor of 2, I do get 10. So all of my angles are the same, and all of my side lengths are proportional. I can get from one rectangle to the other by multiplying by a scale factor of 2 or 1/2, depending which one is the original and which one is the image. So C is our pair of similar shapes. Well, let's go ahead and check D just in case. On D, I can see that I have isosceles triangles. And on the left, I have these sides of 10, and on the right, I have these sides of 5. Well, 10 times 1/2 equals 5. So that should be our scaling factor, 1/2. Well, then on the bottom, I have these side lengths of 6. And if I multiply 6 by that scaling factor of 1/2, I get 3, not 6. Since the side lengths are not proportional, these are not similar triangles. So in order for shapes to be similar, they must have the same angles and then have proportional side lengths that you can reach by multiplying by a scaling factor. I hope this has helped make sense to you, but if you do still have any questions, please feel free to leave a comment below. So in Lesson 8, we had 2 learning targets. The first learning target is that you would be able to critique proofs that use similarity. So, like what we did in practice problem 1, where we read through the proof, and to really help out, we draw it ourselves step by step, and we just pick out whether all the steps really do prove what we're claiming, or if we get to a step and notice that might be a true statement, but it doesn't actually prove what we're saying. And then learning target number 3, I can write proofs using the definition of similarity. This is where you go step by step to prove that using nothing other than rigid transformation and scalings, that you are able to move one figure directly on top of the other figure. If you're able to do that, then you've written the proof and your figures are similar. Remember that similar figures need to have the same angles and proportional side lengths that you are able to get by multiplying by a scaling factor. I hope this helps make sense of Unit 3, Lesson 8, but if you do still have any questions, please feel free to leave a comment below. In the bottom left, you'll see another video that YouTube thinks you'll find helpful. In the bottom right, you'll see the subscription button for the channel. It would really help if you would give that subscribe button a hit. give this video a thumbs up, and if you are interested in one-on-one tutoring, you can check out the homepage for my channel, and the information is there or down in the description below. I look forward to seeing you in the next lesson.